Hello everybody, welcome back to our next lesson. Today we're going to be looking at the graphs of the 6 trigonometric functions. This begins on page 15 in your notes. And actually the first 2 pages, 15 and 16, they just touch on 4 trigonometric functions. We're not going to be spending a whole lot of time on these. I'm not going to be asking you to graph these on a test or on a quiz, but I am going to be expecting you to recognize them. All right. So you could see these on perhaps a multiple choice test or something like that. Now have a look at excuse me. Here's on page 15. Here's the graph of y equals the tangent of x. Now look at that. You can see that it's basically a series of curves starting at the top left going to the bottom right. All of those pieces they're the same exact size, the same exact shape, which I guess means they're congruent, aren't they? But do you notice that the graph has asymptotes to it, vertical asymptotes? Now you've seen asymptotes before when we did conic sections. Well, the asymptotes here for these trig functions, they behave in exactly the same manner. An asymptote is a line, a straight line, that a curve gets closer and closer and closer to, but never ever touches. So each one of these pieces here on the cosine graph that you see, each one of those little curvy parts, they actually go up and down forever and ever and ever and ever. And they're getting closer and closer to those vertical asymptotes, but they're never ever quite reaching it, okay? And that's what the tangent graph looks like. Now, why is there a vertical asymptote, for example, at pi over 2? Well, remember now, pi over 2 is basically the same as 90 degrees. It is 90 degrees. And I'd like to point out that in this unit, when we're doing the graphs, by the way, they exclusively use radians for the measurements on the x-axis. They will not be using degrees. So please make sure you're comfortable using radians. For example, 2 pi, that's 1 complete revolution of a circle. Or if you were drawing an angle in standard position, it's the same thing as 360 degrees, isn't that? Okay. If you were to find the tangent of pi over 2, put your calculator in radian mode, you would get an error message, meaning that it's undefined. 3 pi over 2, same thing. Negative pi over 2, the same thing will happen. If you try to take the tangent of any of those angles, you'd get an error message on your calculator, which means it's undefined. So wherever the tangent ratio is undefined, that's where you get these vertical asymptotes. Cotangent graph looks very similar. But now notice the cotangent graph actually starts at the top left and goes down to the bottom right. Each one of these pieces. And again, they go up and down forever and ever and ever and ever. And you have vertical asymptotes here as well. But notice that the vertical asymptotes are in different places. Cotangent is undefined for different angles than tangent is. So for example, the tangent is undefined at pi over 2 because there's a vertical asymptote there. Well, the cotangent is defined at pi over 2. In fact, the cotangent of pi over 2, by the looks of this point right here, should equal 0. But the cotangent is undefined at pi. It's undefined at 0 radians. The y-axis itself is another asymptote. It's also undefined here at negative pi, and so on. Now again, I won't be asking you to graph these functions. I'm not going to give you a test and say, here, you go ahead and graph y equals tan x. But I will expect you to be able to tell the difference between the two. For example, I could have a multiple choice test, give you one of the graphs, and say, all right, is this y equals tan x? Is it y equals cotan x? Or is it secant x or cosecant x? And that's the two we're going to look at on the next page. Now, here's the graph of y equals secant x. Notice, now they don't say it here in the graph, but the y values and the x values there, let me just jot them in for you. This is supposed to be 1, and this is supposed to be negative 1. Now what you have there are two horizontal asymptotes, and you notice that the graph does not exist in between 1 and negative 1. The range for secant x is either greater than or equal to 1, or it's less than or equal to negative 1. But there are no values in between. Kind of looks like a bunch of U-shapes, doesn't it? And upside down U-shapes. Yep, that's what it looks like. It's got vertical asymptotes as well. For example, here at pi over 2, there's a vertical asymptote. So if you were to take the secant of pi over 2, you'd get an undefined value. You'd get an undefined ratio. Now, of course, on your calculator, you would type in 1 over the cosine, wouldn't you? But if you type in the cosine of pi over 2, now that's defined. Remember, you can take the cosine of any angle and the sine of any angle. But the cosine of pi over 2, if you type that in, that, ladies and gentlemen, is 0. And that's why the secant is undefined at pi over 2, even though the cosine is defined at pi over 2. Wherever you end up with something over 0, that's undefined. And the cosecant down below that, okay, look at that. It looks very similar, doesn't it? Like a bunch of U-shapes or upside down U-shapes. And this graph as well, in between 1 and -1, there are no points. The range for cosecant is exactly the same as the range for secant, but the domain is different. For secant, remember, it was undefined at pi over 2. But it is defined at pi over 2 for cosecant. You see that? In fact, the cosecant of pi over 2, if you look at that point right there, it's got a y value of 1. So again, I'm not going to ask you to graph these. I do want you to be able to recognize them and differentiate between them. Probably the easiest way to remember the difference between the secant and the cosecant is that the secant actually has a y-intercept. Look, the secant actually goes through the point, goes through the point 0,1, but the cosecant does not go through the point 0,1. In fact, the cosecant has the y-axis being one of the vertical asymptotes. They don't show it there, but yeah, that's another vertical asymptote right there. So again, just be able to tell the difference between them. That's about it. And remember that all of the angles for all of these graphs, they're in radians and not degrees. Now, on page 17, this is a different story. We are going to be looking rather in depth at the graphs of y equals sine x and the graph y equals cosine x. What do they look like? Okay. We are going to be looking at equations basically in this form right here. Not just the simple ones like sine x and cosine x. I'll show you those in just a moment. But you're actually going to be adding parameters to those equations, constants. You're going to be adding a number in front. So it's going to be a times the sine. A is just a real number, can be any number. And then in brackets, instead of just x, like in these equations, what if you had a number in front of the x? What if that was 2x or 3x or 1/2 x? What does the b do to the equation of the base graph? And then finally, you could add or subtract a number after the x term. But it's still in the brackets, okay? It's still in the brackets. And you're also going to be looking at y equals a times the cosine of bx plus c. What will they look like? That's what you're going to be graphing. That's what you're going to be graphing. And also, I'll be giving you the graph, and I'll be asking you to come up with the equations in one of these forms right there. And that's what we're going to do in the next few lessons. You'll also notice now, this is still on page 17. You'll also notice they're actually talking about something called the amplitude and something called the period and something called the displacement or phase shift. And do you notice that you see the A's and the B's and the C's are down there, don't you? You see them there in those definitions. So A and B and C does change those things. It has something to do with them. What I'm going to do right now, I've actually got, I've told you about this website before called Desmos.com. Here you go. Here is Desmos.com. What I'm going to be doing here, I'm just going to graph for you the two base graphs, y equals the sine of x. Oh, look at that, a nice green color. I didn't know it was going to be green. Doesn't matter. But anyway, there's what the graph of y equals sine x looks like. Now, I tried a little while ago to get my ink to work. No, I can't. It won't work. She's asking me to leave the page if I try to get my ink on the go. But can you tell here, look at this carefully, the amplitude refers to the height of your curve, from halfway on your curve to the top, or from the midpoint of your curve to the bottom. And you can see here that for the sine graph, the amplitude is equal to 1. I wish I could use my ink here and show it to you, but I can't. Oh my, too bad. Now, so the amplitude is equal to 1. The period refers to some point on the graph somewhere, like, okay, from there, 0, 0, all the way up, say, to this point. You see that? From the origin to 2 pi, that is one period, because you're starting at a point on the curve and you're going to the corresponding point on the next curve. All right, so notice that they're both on the positive sloping upward. There's the period. The period of, that means how long does it take to repeat? The period of y equals sine x is 2 pi. Now, you won't see a displacement here because this is your base graph. This is your sine x graph, y equals sine x or y equals sine theta, whatever you want to call it. How do you tell if this graph is actually moved left or right? And we don't look at an upward or downward movement. We're not looking at a vertical translation. But it is possible you could have a horizontal translation here, okay? Well, what you do, notice the point that I've highlighted is 0, 0. You have to look very carefully at that point. Notice it's exactly halfway up your curve, right in the middle, but it's on the part of the slope that's positive. It's sloping upward to the right. That is what we're going to call the starting point, or the original point, for y equals sine x. And you can tell by looking at a graph, where is that point? Where is the point that's halfway up your curve, but on the positive slope going upward to the right? And that will tell you what your displacement is. All right, that's sine x. Well, let's try the other one. Y equals cosine x. Oh, and look at that. They've got a nice blue curve there, a purple curve. Okay. Now, don't those two curves look a lot alike? Yeah, they're both known as sinusoidal functions, sinusoidal curves. They're basically waves that continue on to infinity in both the positive and negative direction. Okay, the domain is just anything, all real numbers, because you can take sine or the cosine of any angle. There are no breaks in that curve. But if you look at the cosine graph, you can see that the amplitude there is 1, isn't it, of the base graph. If you want to find out what the period is, well, now you can do that several ways. You could pick this point right there, and I'm using my highlighter. I am able to highlight a point. So if you went from 0, 1, that's what we call a maximum. That's a maximum value right there, because it's a relative maximum, because it's on the part of the curve that's kind of the highest point for all the points that are close to that. And if you go all the way across to the right on that curve until you hit the next maximum right there, you see that? Now look at your x-axis. What's that distance? From one maximum to the maximum right next to it, the distance is 2 pi. I wish I could use my marker here. I wish I could use my ink and I'd actually draw it in for you. But you can see from 0 up to 2 pi, that's exactly one wave. So the period of the cosine graph is also 2 pi. They're both the same. So they have the same amplitude and they have the same period. All right, the base graphs do. Now, what about if you were going to have a movement, a sideways movement? That's called the displacement or the phase shift. Well, in this case, the point that you pick as your original point, and you sort of test it to see if it moved left or right, is the point that I've highlighted right there. You see that? It's the maximum, 0, 1. When you have the graph of a cosine function, a sinusoidal function in terms of cosine, look for that maximum. Because if that maximum has moved left or right, that tells you your displacement, okay, of the cosine graph. All right, so let me just, I'll just clear those out of the way. And I'll leave this graph paper there because I think we're going to come back and use that again now in just a moment. Right here, this basically tells you, right there, how is A and B and C related to the amplitude and the period, and also the displacement. These formulas right here, the amplitude, whatever number is in front of your sine, the absolute value of that is your amplitude, because sometimes it's negative. Now, if it is negative, remember that refers to a reflection in the x-axis, but most of the examples we're going to be looking at, A is going to be positive. The period is 2 pi. divided by whatever number is in front of the x. All right, that's for these functions up here, if they're in this form. You look at that b, take 2 pi and divide it by b, and that will be the period of the new function. And for the displacement or the phase shift, here's how you calculate it. Look, it's negative c over b. And in fact, for the next few pages, they just talk about the amplitude. There's a definition. 1/2 of the vertical distance from a minimum to a maximum. That's another way to think of it. Or think of it as the distance from the middle of your graph, the midpoint, up to either the top or to the bottom. There's the period, the length of one cycle. The calculation will be 2 pi over b, and the displacement means that the amount that the graph shifted to the left or to the right. Some courses also refer to a vertical shift or a vertical translation, but this course doesn't do that. Okay? And right there, this is page 18. And there's the graphs that we just looked at. You could even make up a table of values if you wanted to and graph those. I mean, that's what some courses I've taught, they actually had that as one of the objectives, was that a student would make up a table of values and sketch the graph of sine x and the graph of cosine x. But if you look at these carefully, now I can use my ink. Look at that. See the distance from the middle of your graph to the top? That's your amplitude, that height. So the amplitude is 1. Or you can think of it as a distance from the middle of the graph to the bottom. But it's still 1. You see that? The red graph is your sine function. So here is 1 point on your curve. If you sort of follow the curve until you hit the corresponding point in the next cycle right there. You see that? That distance, that's the period, and that's 2 pi. The period is 2 pi. And it's also 2 pi for your cosine graph, because you can go from maximum to maximum for your cosine, but look at that, it's still 2 pi. And finally, when you're thinking of, like I was saying just a moment ago, starting points. If you want to tell if the graph has moved left or right, then what you do is, for the sine graph, use 0, 0. 0, 0 is the starting point for sine. And this point right there, 0, 1, that's going to be the starting point for your cosine graph. All right, so when we see some graphs in just a moment that are actually translated horizontally, I'll bring this up again. And that's exactly what you're going to be looking for. And then if we go to page, right here, if you look carefully, this is something that I just mentioned a moment ago. For the base sine and cosine curves, in other words, before they're changed, before they're moved, amplitude is 1, the period is 0 or 2 pi. And then now if it's the base graph, then it hasn't been shifted anyway. The displacement is 0. Okay? And here's, ta-da, there's the two forms that your equations are going to take. And you're going to be looking at your A and your B and your C. Now the next few pages, I mean, if you look at these carefully, they explain exactly how does the A and the B and the C, how do they change your graph? Now A, remember, is the number in front of sine or the number in front of cosine. And I can show you an example of this on Desmos as well. So for example, if you graph y equals 3 times the sine of x, what's that going to do? Well, let's have a look. Y equals sine x, there's your base graph. We saw that just a moment ago. And now if I graph y equals 3 multiplied by the sine of x, there it is. See that? Now it probably doesn't change color, no. But you can see that the height of it has changed. The amplitude now, it was 1 for the base graph, well now it's 3. But if you look carefully, the period has not changed. And it hasn't been shifted left or right because that starting point, 0, 0, right there, can you see it? 0, 0. By golly, it's still there, isn't it? It's still at 0, 0. That didn't move, so there is no horizontal translation here. There was no stretching. That's what changes your period. But it was stretched upward. No horizontal stretching, I should say. All right. Let's go back into the notes and say. So that's what the A in front does. It just changes the amplitude. So if you look at this graph right here, okay, let's answer these questions. For example, number 1, page 19. The amplitude is going to be 3 because that is the number in front. The period has not changed. The period is still 2 pi. And you can tell that by looking at the graph right here as well. Look, there's 1 point, and here's the corresponding point on the next part of your curve. There's one complete cycle, and it takes 2 pi radians to go through one complete cycle. The displacement, 0 right here, because the original starting point, 0, 0, did not move. Here's another example. Y equals 1/2 times the sine of x. There's your a in front, right? Well, look at that graph. And now you can see that it only goes up, I don't know if you can clearly see it, but it only goes up as far as 1/2 and down as far as negative 1/2. You see that? So in this case, the amplitude is 1/2. It's 1/2. But the period has not changed. It's still 2 pi, and the displacement is still 0. And that would be true even if you put the cosine in there instead of sine. Same thing would be true. On page 20, what's the effect of changing the b? Now, the b, remember, is the number in front of the x. Okay, that's what happens there. And we saw the formula for that a moment ago. There's your formula right there. So remember now, the number in front of your x, that's what they're calling b. So what's the amplitude here? Well, what number is in front of the sine? You know, there's a number there. You just don't see it. There's a 1 in front. So the amplitude here is 1. The period of this graph, if you look very carefully, is 2 pi, if you calculated it. B is 2, so if you divide 2 by 2 pi by 2, by golly, look at that, it's pi. Now look at the graph there. Are you convinced that the period of this graph is really just pi? Well, let's go through a complete cycle now. This is sine. So let's start right here at this point, 0, 0. If I go through one complete cycle, I go up and I go down, and I come back to the point corresponding on the next piece of the curve, the corresponding point. And that distance from here over to there, if you look carefully at your x-axis, that is pi. But the graph again has not been shifted because there's my starting point for sine, 0, 0. And by golly, it's still at 0, 0, isn't it? So the displacement here is 0. There's an example down below. Okay, this is cosine. Doesn't matter. Sine and cosine behave very much the same way. The number in front of the cosine here, remember that's your a. Well, I don't see a number there, but there is a number there. There's a 1 there. So the amplitude is 1. Sure enough, look at that. There's your 1, and it goes all the way down to negative 1. The period, let me see. Let me just look at the graph first and get the period. Here's 0. Okay, think of that as the max. And I'll follow the curve along, follow the curve along, follow the curve until I hit the exact same point on the next curve. Now, what's that distance from here over to there? I like to pick the y-intercept as my first point, by the way, because then you just have to look at your x-intercept, and whatever that x value is, that's your period. Well, by golly, look at that. The period is 4 pi. If you did the actual calculation, watch what you would do. You'd have 2 pi divided by b, which is 1/2. Now, dividing by 1/2 is the same thing as multiplying by 2, remember? In fact, let me just show you what I'm doing here. 2 pi divided by 1/2, and you know how to divide with fractions, right? Multiply by 2 over 1, and look at that. There you go. So yes, the period is 4 pi. And the displacement here again is 0, because remember, for the cosine graph, the starting point we said was going to be that maximum, right, at 0, 1. And it didn't move, did it? It did not go left. It did not go right. It's still right on the y-axis. And then on page 21, now they want you to see the effects of c. And here's the c right there, any number added or subtracted onto the end. And by the way, I can still see there's a b right there. Look, that's 2. A in front, that's a 1. All right? Look at the graph. The amplitude, clearly from the graph, is equal to 1, isn't it? Yeah, the amplitude there is 1. The period is 2 pi divided by the b, which is in front of your x. That's 2 pi divided by 2. So the period should be pi. And if you look at it carefully, now how would you get pi? Well, I'd pick the y-intercept right there, and I'd go right through the curve, go right through one cycle until you arrive at approximately the same point on the next curve, which is there, and you look straight down. If you pick the y-intercept, this is always true. Look at that. There's your period. It is pi. It really is pi. Or another way you could do it, if you pick the maximum here, that value right there. Now, it's kind of hard to tell because halfway between 0 and pi over 4, that's pi over 8. This is just another way to get the period. And this maximum right there, well, what's halfway between pi and 5 pi over 4? Oh my goodness, that would be 5 pi over 8. See that? So you'd have to subtract there. Wow, that's kind of tricky. Pi over 8, 2, 3, 4, 5, 6, 7, 8. Oh, sorry, that's 9 pi over 8. 9 pi over 8. Be careful there when you're doing the subtraction method. The displacement. Now, look at this carefully. Can you tell what the displacement is? Now, I want you to see it graphically, but I also want you to see it using your equation, using your formulas. The displacement for the sine graph, remember we said the sine graph the starting point is 0, 0. That's what we said, wasn't it? And remember, that's halfway up your curve, exactly in the middle of the curve, but it's on the positive sloped part. So this would not be a starting point because that's on the negative slope part. Don't use that. This would be a good choice right there. You see that? That would make an excellent choice for your starting point. Now, what is that value right there? Halfway between 0 and negative pi over 4. I wish they had... I wish all the values were placed on the x-axis here. That's actually negative pi over 8. You see that? That graph is the base graph shifted pi over 8 units to the left. So we say that the displacement is negative pi over 8. Now you could also, by the way, for displacement, you could also pick a point like right there. As long as it's one of the x-intercepts, halfway up your curve, and it's on the sloped positively part, then it works fine. That would also be your displacement. Now, if you use your formula, watch this. Negative c over b. Let's see what it gives us. C is pi over 4, so negative c would be negative pi over 4 divided by b is 2. So negative pi over 4 divided by 2 is the same thing as negative pi over 4 times 1/2. Most people just type that into their calculators, by the way. And I'll just come up here and write that down. Straight across now, that's how you multiply fractions. Negative pi over 8. Look at that. That's your displacement. And that's exactly what we said over there. And that's how you can tell your displacement. Okay, what do we have left to do? Well, that's pretty much it for this lesson, I think. You will notice that down below that, everybody, now they have some practice questions right here. So on pages 21 and also on page 22, they're giving you a series of equations, and what they're asking you to do is determine the amplitude, the period, and the displacement for each of these functions. All right, and they want you to use the formulas. So for the amplitude, it's just whatever the absolute value of the a is in front. I think they're all positive here anyway. But if you do see a negative value in front, a negative a, just take its absolute value. All right, and the period, the way you calculate the period is 2 pi divided by whatever the b is. The b is the number in front of your x, remember. And for the displacement, your formula would be negative c over b. And c is the number on the end, like those. And b, again, is the number that's just in front of your x. So if I just did number 3 really quickly, watch this. My amplitude is equal to, well, whatever that number there is. It's 1/2. My period is equal to 2 pi over b. So in this case, that would be 2 pi divided by, and there's my b right there. Look in front of the x. So divided by 1/2. Now, be careful because you're dividing by a half, which is the same as 2 pi multiplied by 2. So that's going to give you 4 pi. There's your period. And finally, for the displacement, let me just come up here and show you how to do that. It's negative c over b. So for the displacement in this question, you'd have negative pi over 4. Notice that c is negative anyway. Divided by 1/2. Now what would that give me? Let me just erase some of this, make some room. And I'll stop this video then after this, and I'll let you go ahead and try some of the other ones. So this would be equal to pi over 4. Remember now, negative becomes positive. Divided by a half is the same thing as multiply by 2. And so that'll give you 2 pi over 4, which you can reduce to pi over 2. Positive, so this graph has been shifted from the original cosine graph. This graph has been shifted pi over 2 units, which would mean to the right. So that's number 3. That's the one I just did right then. So you try the other ones, 1, 2, 4, and the practice problems on page 22 as well. And when we come back in our next lesson, we'll actually start graphing some of these, okay? Now, if you don't have the textbook printed off, well, I hope you do, but you're going to have to get some graph paper somewhere and plot them yourself, plot the axes yourself, and then you can actually go ahead and graph it, okay? So I'll stop there, and I'll see you in our next video. Bye-bye.